so on. And it's a brick, you can see. And that's why it's called gravitation. When you pick it up, you know everything you need to know about gravity. And I was going through all the equations, and I could see that the physicists were starting to get upset with me. I was, kind of going through, the way they think of the universal dynamics and the universal expansion and all this. And I finally said, okay, if I understand your model right, and I opened gravitation on page 719, and I said, if this is correct, then the universe is something like this, which they show you after about 1,000 equations. The model for our universe is a balloon with pennies glued to it. So what you do is you take a balloon, you take a bunch of pennies, and a glue gun. And you glue the pennies to the balloon, and the pennies represent galaxies. And then as the balloon inflates, the galaxies move away from each other, generating the universal expansion we observe with the Hubble. It's called the Hubble constant, or the Hubble expansion, and is observed by various modalities, including telescopes. And so I'm going through this with them, and you got to realize these guys are very accomplished physicists, and they're looking at me going, oh my God, this is like kindergarten stuff. If you don't know this stuff, you should go back home and study a little more before you waste our time. And so I was like, well, what I want to know is where is the equation, because I really looked through all your stuff, and where is the equation for this guy? And, the room became quiet. And I was saying, well, this is definitely a component of the dynamics that are going on. And I said, if you keep drawing, if you don't stop at the face, and you keep drawing the rest of the guy, you'll notice that when the balloon expands, the lungs contract. For every action, there's an equal and opposite reaction. First law of physics. That hurt. Everybody had a blank look on their face, and the room became so quiet you could hear a pin drop. And I could see my dear friend and sponsor across the room going, oh, you're doing damage. Kind of obvious. Completely missed. Obviously, if the universe expands, then something is contracting. And that dynamic of expansion would be a feedback, right? Expand, contract, expand, contract. And it would have a very specific topological structure, meaning it would look in a very specific way. It would have very specific dynamics for things to be able to expand and then contract and so on. So, when you think about it, and I was thinking about it for years, if you radiate, if you look at the universe, you find that everything in the universe radiates. What does it radiate in? In the vacuum of space. well then, the vacuum cannot be thought of as empty, can it? Because no energy is lost, no energy is gained. So if all the suns, all the stars, all the galaxies, all the black holes, everything we see radiates into the vacuum, then the vacuum must be full. Full of energy. And it was clear to me that then the vacuum must be the contractive side of the event horizon, the contractive side of the structure of reality, the part we don't see. Why? Because it's contracting towards infinity, moving away from us. It appears to us as vacuum. So I was puzzled about that, and I remembered my first class of physics. So again, you know, I'm all excited. Now I'm about 16, and I'm going to my first class of physics. Well, actually, I'm like 14 or, 15, something like that. And I'm like, oh my God, today I'm going to go into my first class of physics. I'm going to learn everything there is to know about atoms and reality. So when I sat, the first thing I did is put my hand up. And, the teacher didn't know me better at the time, so he asked me what I wanted. And I said, what is an atom? I was surprised to hear the response. I thought, oh, he's just going to spell it out. What the heck is an atom? And he said, oh, that's way too complex for a first physics lesson. And in fact, we are not quite sure what an atom is. I was like, huh? You mean that in all of the years of physics that have been going on this planet, you guys still don't know what the heck is an atom? How can you tell what anything else is then? Right? And so I was like puzzled, but one thing he said is that one thing we know is that the atom is made out of 99.99999% space. And I went, oh, space. Mostly space. Everything you see, everything you touch, everything is mostly space. 99.99999%. That includes you. You are 99.99999% space. And it was like, wait a minute. That the universe is connected by a non-seen force, right? What would be the thing that would connect all things? Space. That's the only thing that's everywhere. And that's the only thing that all energy is radiated into. So I started to think, maybe it's the exact contrary. Maybe the atom is just a result of a division in space. Aha! Like the fractal structure we just saw. Divisions of space to infinity. Now it starts to look a little different, doesn't it? Is your brain starting to hurt? That's okay if it does. It's normal. Don't panic. It'll get better. But imagine you're doing music. You need silence to be able to cut it, to make music, to make a beat. If you're making reality, you need space to define the reality in between. So space, reality could be just various resolution, right? Various divisions of space in a fractal structured vacuum, which is some of the math we just published recently. It's becoming extremely popular, the concept of a structured vacuum, energetic structured vacuum. This is in advanced physics. So I dug a little bit more after that first class in physics, and I found something that blew my mind.